What's up, y'all? Welcome back. This is a new video with Meds Mnemonics. And if you like the content that I've been pumping out, click the like button. Or if you want to give me a better for a litmus test, just click the subscribe button so I know that I actually should start making more videos and you guys like what I'm pumping out. Without further ado, let's get rolling. You guys can read? Okay, so this is just a medical disclaimer, meaning that this is purely just for fun and educational. And if you have a serious medical problem, go see a medical professional. Please don't sue my ass. I am going to swear, it's inevitable. I can't help it. For that, I'm not sorry. And like I always say, tough shit. Okay, so today's topic is going to be on EKGs. This is essentially just going to be like an overview of basis of it. There are a lot of other good videos on YouTube land that essentially goes through this more in depth. I figured that this was a good video to just give you a basic understanding and just a little bit of an overview of what EKGs are all about. Okay, so this is what the overview is going to look like. We're going to go over some basics. We're going to be able to calculate the heart rate, look at all the 12 EKG leads, where they are and where they're from in the EKG when you actually look at one. STEMI location, as in like where's my heart attack. Axis deviation, this question does get asked a lot, so I thought I'd include in here and how to actually do that. And then there's going to be a method at the end on how to actually scan an EKG when one is handed to you from your preceptor, how to actually go through it step by step. So let's get going. Okay, so with EKGs, so what the hell is an EKG? So essentially what it is it's called an electrocardiogram. This either could be ECG or an EKG. And essentially what it is it's a machine that actually gets hooked up with electrodes to your body. No, it does not shock you. But what it actually does is it actually looks at the electrical conductivity generated by the cardiac myocyte cells. And on the next slide, I'll actually show this more in depth. So the whole main point of an EKG is to detect the positive charge movement towards the positive electrode. I know during physics, it can get a little overwhelming as to like which charge is moving which direction and what is going to actually propagate. But in this sense, it'll actually make sense on the next slide why this is important, that it is a positive charge moving towards a positive electrode. And then the electrodes here at the bottom are going to be 1, 2, 3, AVL, AVR, AVF, and then V1 through V6 for a total of 12 electrodes. Okay, so real quickly, what I'm going to explain is the positive charge moving towards a positive electrode. So here you're going to have a myocyte cell, which is going to be a heart cell. And typically a cell is at a negative resting potential. So if you looked at like an action potential in a biology textbook, it'll say it's like around like negative millivolts. So in this case, it's going to be negative. But if it's stimulated and actually gets, instructed to become positive through ion channels are going to go open and ions are going to go inside, and you're going to see that a positive charge is going to go towards the center and the inside, turning the cell from a negative to a positive, as you can see here. So now the cell is positive. Now, if you were to line this up with two electrodes, and if you can see here, I'm going to use my cursor, this is one electrode that's going to be a sticker on your body, and then this is going to be another one. And what it's going to do is it's going to measure the charge moving in this direction. So as I flip through further through this slide, you're going to see this positive. Next, cell will become positive, positive, positive. Guess what? Another positive. That's it again. Another positive, positive, positive. So essentially what's going to happen is this positive charge, as it's going from left to right, it's actually going to pick this up on the EKG. So you can see on the right here, I do have a little diagram that says, well, it doesn't say anything, but that shows what you're going to do is as this positive charge is coming from the right to the left, it's actually going to pick this up. So as this propagation of positive charge moves between the two electrodes, this is actually what's causing this deflection up. And then if it were going the other direction, it would go down. So you can see here that when it's going from left to right, this positive charge moving in this direction, it's going to have a positive deflection on the EKG. So essentially what I just said, positive charge movement towards the positive electrode when it depolarizes. Inside becomes positive. Okay, so now we're going to go over some heart basics, okay? So to the right here is a very delicate image that I created really quickly. I'm sorry if it looks like shit. So when you're actually facing someone and they're looking at you, meaning that it's a mirror image, this is what the heart is going to look like. You're going to have the atriums, so they're going to be on the top, and you're going to have the ventricles on the bottom, and you're going to have left, right, and left and right. And the way you can remember this is through a little quick mnemonic over here, is that you're going to have the top part, which is going to be the atria. So think of an A sits on top of a table, and then V actually looks like it's holding up two arms, or you can think the bottom of a heart, like a Valentine's heart. And then The actual electrical charge movement is going to be through a sequence of four main parts, which is going to be the SA node, which is sino-arterial node, atrial node, and it's going to be the AV node to the bundle of His to Purkinje fibers. Sorry, I can't speak today. So you're going to see it here with the heart that I have down here is that it's going to start from the SA to the AV to the bundle of His to the Purkinje fibers and then back up, and it's going to shoot back around. And the way you can remember this is through the mnemonic of son of a bitch, just pump. So you're going to have the SA node, AV node, bundle of His, and then Purkinje fibers. And over here, just one more time, this is actually what it looks like when the electrical, I guess, propagation going from one electrode to another. This is the overall main direction that it's going. And this will make more sense when we actually look at the individual leads. But you can see down here on the right, it's going to go from one electrode, one of the stickers on the body, to the other sticker on the body, and the charge is going to move in this direction of a positive charge propagating in this direction. And it's going to be through the SA-AV bundle of His to Purkinje fibers. Okay, so the basic electrode. So right here, this is essentially going to be one sliver of the EKG. So this is the very standard EKG and how it actually looks. And you're going to have the few different parts here. So you're going to have the P, the Q, the R, the S, and then the T. So these are going to be the five main parts that are going to be part of the standard part of the EKG of what you're looking at. And then you're going to have the actual intervals. So you're going to have from what's called the P to the R. So from P, where it starts, to the R is going to be PR interval. And the length of it should typically be one big package. So just think the P to P here. That's going to be important later in the next slide. It'll actually become more obvious when we get to that part. So the next part is going to be QRS, as you can see from Q to the R to the S. Just remember, QRS is easy as 1, 2, 3. There's 3 letters, therefore it's 1, 2, 3. It should not be bigger than 3 boxes. The next one is going to be QT intervals, so from the Q to the T. And I just remember QT pi, so 2 packages, meaning that from here to here, it shouldn't be bigger than 2 packages. Essentially, shouldn't be any more than double the PR interval. And I have that in wording over here on the left. So intervals, PR is going to be less than 1 big box. And in 1 big box, there's going to be 5 little ones. Again, this will make sense on the next slide. QRS is going to be no bigger than 3. And then QT is going to be less than 2 big boxes. So this will make more sense when we get to the next slide. Well, just kidding. It's actually on the next part coming. So the main parts, I'm just going to point out the 3 main big ones, and I'm just going to click through this. So you're going to have the P, which is going to be the arterial depolarization, meaning that the top part is going to contract. That's what this P little bump here is here. And then the QRS is actually giving me the bottom part of the heart, which is the ventricle depolarization, where the bottom part squeezes. And then T is when the ventricle actually repolarizes, meaning that it becomes negative again. Okay, so now when I was talking about small and big boxes, this part's actually going to make a little bit more sense. So this is called crunching the numbers. When you're taking your test, you're taking your boards, they are going to at times ask you to calculate the rate or have you just kind of guesstimate like how fast is the EKG? Is the rate really fast or is it really slow or is it normal? So that's essentially what this slide's going to be all about. So what I'm going to do is take one of these big boxes that's in red over here, and what I'm going to do is just kind of zoom out. So if you look at this big box, it actually has, so this whole part right here with the thickened lines, when you zoom out, it is a big box. This whole thing is a big box. On the inside, there's 5 of them. And one little one is 0.04 seconds, meaning that it's 40 milliseconds. And you can remember the small box has 4 walls. So you just remember that it's 0.04. So that's this part. If you wanted to measure this whole thing, which is one big box, just think that you have 2 big balls. If you're a male. Sorry, if you're not a male, then obviously you don't have those. So if you have one big box, then it's going to be 0.2 seconds, meaning that's 200 milliseconds. And I'm going to have all this in writing up here on the left, so it's a little bit easier to understand. So one small box is going to be 40 milliseconds. 5 small boxes in one big box, thus, do a little bit of math. Just essentially think 5 times 4 is going to be 2, and that's, 20. And therefore, that's going to be 20 milliseconds in one big box. Okay, so this is what they were going to ask on your exams, like how do you determine heart rate? So I'm going to show you do the quick and dirty way, and then I'm going to show you how to actually like calculate it to a T. So first off, you have to pick somewhere to start. So in this diagram here, or in this image, you need to pick at the point of the R. So this is where you start right here. Okay, and then what you want to do is you want to count how many boxes, and if you use the thickened lines, you want to count over, and that's how many you want to get to the next one. You stop. Okay, exactly what I said. Count the big boxes to the next R point. Then you want to take the number 300 and then divide it by the number of big boxes that you actually counted. So I'm going to actually just go through this and further go forward with, sorry, I'm very tired. Go forward with the slide so you can see that how many boxes you're actually going to select. So you're going to have 1, 2, 3, and then a little like 4-ish. It's not completely 4 boxes. It's a little bit less than that, but you can just essentially say that it's 4. So yeah, the final number is the heart rate in beats per minute. And then what you're going to do is take the 4 big boxes, and then you're going to have 300 divided by that number, which is going to be 70 beats per minute. So if you want to do it more specifically, what you want to do is you want to count all the little boxes. So like I said, there were 5 little boxes in 1 big box. So if you count here, you have about 1, 2, 3, 4, and a little bit in change. You're going to have 4 times 5 is 20 plus the 2 left over. So that's what I have right here. 4 big boxes times 5 is 20, and then plus is 2 small ones. And then you take the number 1500 and then divide it by all the small boxes that you just added up, you're going to get your answer. So in this case, it'd be 1500 divided by 22 equals 68.2 beats per minute, presto. That's how you determine the heart rate when the EKG doesn't tell you at the top or you're being asked on a test question. Okay, so why does this matter? The reason you want to be able to calculate the heart rate really quickly is you want to be able to look at it and look from, as you can see here, from point to point. You want to see really quickly, like you want to go like 1, 2, 3. If it's more than 3 big boxes, then you know it's going to be 300 divided by 3 would be 100. It's under 100 beats per minute. You need to really be able to train your eye to look at an EKG to see if it's actually really fast or actually really slow. So a normal heart rate is going to be between 60 and 100 beats per minute. Now, if it's tachycardic, think top, meaning that it's above 100 beats per minute. And then there's bradycardia, which is think below, which is below 60 beats per minute. And a quick little mnemonic is a B looks like 6, so 60 and below would actually be bradycardia. So that's why it's important to actually really quickly, by just licking your finger and sticking it in the air, is it fast or is it slow? Okay, so now we're going to go on to the leads. So real quick, this is a diagram right here of obviously the heart, and I'm going to talk about leads 1, 2, and 3. And these are going to be the bipolar limb leads. So what they'll do is when you go in the hospital or you go to the doctor's office and they're actually going to do an EKG on you, what they're going to do is they're going to slap a bunch of stickers on you. So a sticker would be over here, a sticker's going to be over here, and a sticker's going to be down here. And what they're going to do is they're going to communicate with each other, is they're going to show that this is going to be lead 1, it's going to be going in this direction. This is going to be lead 2 going in this direction, and then lead 3 is going to go in this direction. So just remember with lead 1, you've gone east, meaning that it's going to go from the left to the right. This is lead 1. Lead 2 is going to go towards your toe, more specifically towards your left toe. And lead 3 is going to go towards your right knee, so it's going to go in this direction. So if you just draw this upside down triangle and go 1, 2, 3, these are the 3 leads that you have. So what you're going to want to do is when you're evaluating a 12-lead EKG, essentially you want to jump straight to lead 2, and I actually have a whole slide on how to methodically go through an actual whole full 12-lead EKG, but specifically when you print out a rhythm, whether it be like someone on the ambulance or they want to look at one specific strip, it's going to be lead 2 because this goes in the same direction as electrical propagation of the heart. So you can see here that you're going to have the charge, like I said, going from this electrode to this one, and it moves in this direction across your heart. Well, that is the same direction as lead 2 because lead 1 would go more this way, lead 3 goes in the opposite direction this way. So lead 2 is the one that actually matches up fairly well with the actual propagation of the charge, hence why we pick lead 2. And then when you look at the 12-lead EKG, it's going to have 1 through 3, R, L, and F, and then 1 through 6 is what you're going to see of all the strips when you're actually given the full sheet of paper. And we're actually talking about these 3 right here. Okay, so more leads. So now we're going to talk about the augmented limb leads, which is going to be AVR, which is going to be here, which is going to be AVL, and then AVF. So for the AVL is going to be left, meaning that this one's going to be going up towards the left shoulder. AVR is going to be going backwards up to the right shoulder, and then AVF goes down towards your feet. So I hope that's pretty not counterintuitive, but pretty intuitive from just the names. So if you just look at what it's actually called, that's the direction it's going in. So the R is for the right shoulder, left, L is for the left, it's going that way, and then F is going to be for the foot. So an example, AVL charge is traveling to the left hand or left shoulder. And then when you look at the actual 12-lead EKG, these are the ones we're looking at and it goes in this order from R to L to F. Okay, these are the last leads, I promise. So this is going to be the precordial leads, and these are going to be from V1 to V6. These actually get strapped all the way across your chest and wrap around like the bottom of the U. So it's going to be V1 to V6. Like I said, they go across from the left portion of the chest. And then what we're actually looking at is we're looking at it here from V1, V2, V3, V4, V5, V6. And it's going to wrap around like this. So if the middle of your chest is right about here, your heart's over here, they're going to stick them on in order like this. Okay, so I put this in here of saying like, where's my heart attack? So when you actually look at a 12-lead EKG, you're going to be looking for what are called ST elevations, meaning that between the S and the T segment, it's actually going to elevate, and it's actually called what looks like a tombstone, because if you have a tombstone, you're likely going to have a fatal issue, therefore you might die. So what you want to do is if you actually can see patterns of which ones have the tombstones, you can actually figure out what part of the heart is actually malfunctioning, hence, where's my heart attack? So what you can do is if you draw out 1 through 3, AVR, AVL, AVF, and then V1 through V6, if you draw these parts out and circle it just like I did right here, this actually can tell you what part of the heart is actually malfunctioning. So for an inferior problem with the heart, it's going to be an issue of 2, 3, and AVF, which is highlighted right here in the same color. For the septal, which is going to be here, this is going to be the S, which you just wrap around here, which is going to be V1 and V2. If it's anterior, meaning towards the front of the heart, it's going to be this upside down A. So it's going to be AVR, V3, and V4, and a little bit of V1 and V2. And then anything else that's not touched is going to be in green. So anything lateral, meaning more on the left side of the heart, it's going to be lead 1, AVL, and then V5 and V6, which intuitively makes sense because as you remember, lead 1 is gone east, actually goes towards the left of the heart. And then AVL goes towards the left hand or left shoulder. And then V5 and V6 is also on the left side of the part of the body. So therefore, if there was a problem over there and had the tombstones, this would make sense that that would be a lateral MI, which is a myocardial infarction, another word for heart attack. So the way to remember this is that for the inferior, this part kind of looks like a fallen over I. If you were to fill out the rest of it to make a capital letter I, this would be inferior. Septal is a swirl of an S. The anterior MI is just an upside down A. And then anything else that's not boxed in or highlighted is just the rest. That's going to be a lateral MI. And then I have down here what STEMI means. So it's ST elevation, myocardial infarction. So the ST elevation, meaning that segment of the EKG, I really wish I put it in this part of the slide to make it more simplistic to see what the hell I'm talking about, is that one portion of the EKG is actually elevated, and then myocardial infarction means heart attack. And then if you were to just write this out and then draw these simply when you're doing it with the pen, just write 1 through 3, R, L, and F, and then 1 through 6. Then you just box this part off, draw an upside down A, and then circle the S, and then you know the rest is going to be a lateral MI. So it's just a quick and easy way that if you're being tested on this stuff and you're trying to figure out like where is the actual STEMI or occlusion in the vessels, what are called the coronary arteries of the heart, this little diagram will actually help you get there really quickly. So here's an example. If you were to have an EKG strip, I know this is not a real one, I actually had to draw it because trying to find a good one to illustrate this without copyright was a huge pain in the ass. Actually, I think drawing this and the amount of time it took me to draw this was actually a bigger pain in the ass. So what you want to do is look for these quote-unquote ST elevations / tombstones. So I'll give you a second to look through this and see if you can pick it out. All right, so real quick, here are the arrows where the actual ST elevations are. So, like I said, if this is a normal EKG, the S is going to be from here to the T here. And this part is not elevated, but you can see in this one, it's clearly above baseline. So it's in 2, 3, and ABF. And if you remember from the mnemonic, this is going to be an inferior MI, meaning that it's on typically the right side and below the bottom part of the heart. So you can see that 2, 3, and ABF is a fallen over I. That's what you're going to be doing when you look at an EKG for ST elevation / tombstones. Okay, so on to axis deviation. So this question doesn't get asked all the time, but it's actually kind of good to have an idea if, like essentially how to determine axis deviation. Meaning if it's left-sided versus right-sided, it can actually tell you or give you clues if the heart is enlarged on one side or the other or both. Because if there are more cells, meaning if one part of the heart is bigger, it can be through hypertrophy, which means bigger size, then you're going to have more charge. Therefore, you're going to have more stimuli from that side, from all the leads. So this can tell you if someone has a problem with the left side of their heart or a problem with the right side of the heart or both. So real quick, I'm just going to show you like what this diagram is and just kind of split this up. So the x-axis here is going to be lead 1, which is going to be right here, which is why this is highlighted in red. And then the y-axis is going to be ABF, which is this guy right here. So when you're going to do axis deviation, you're going to look at these two main leads. You're going to look at 1 and then ABF. And then if you were to look at the EKG and it's something were positive or negative, as you can see for lead 1, positives in this direction, negatives in this direction, and then for ABF going down is positive and then negatives going up. So this will make sense when I click through this. So like I said, you want to look at leads 1 and ABF. And then you want to sum the QRS complex above and below both leads. I have an example on the next slide of what the hell that just, what I just said and what that actually means. So to determine the axis, if they are both up, meaning if the spiky part of the EKG is actually, if they're both pointed up, then it's normal axes. Because if you look at it here, if it's positive in lead 1 and it's positive in AVF, it's in this normal range. And then if lead 1 is the only one up, meaning this is positive and it's negative, then it's going to be left axis deviated because this is going to be negative AVF here. Now, if the AVF is positive and lead 1 is going to be negative, then it's going to be a right deviation because you're going to go in the positive direction of AVF and then you're going to go into the negative portion here of lead 1. And then if they're both negative, because this is a negative here in lead 1 and this is a negative here in AVF, it's going to be extreme deviation. All right, so what I'm going to do is I'm going to go through this, what's called the hands method. This will make it a little bit more sense when you're actually trying to figure out the axis deviation, if there is one at all. So again, you're going to look at leads 1 in AVF. So like I said, you're going to be looking on the EKG and you're going to be looking at the QRS complex. You want to get the sum if this is all up or if it's down. So in this case, for a normal axis, they should both be up. So this is going to be up, and you're going to look at AVF, and this is going to be up. And if you have your hands out in front of you, this should indicate you that they're both up, okay? So that would be a normal axis. Okay, so now if it was a left deviated axis, whichever hand is still up, and if the other one's down, it's the hand that's up is what the axis can be called. So in this case, because if you have your hands out, the left one is still up, and the right one is down. Therefore, this one is the left deviated axis. And then for the right deviated axis, as you can tell, is going to be the opposite. So the right hand would be up. And then an extreme deviated axis, meaning that they're both down, is going to have both hands down. So I'll show you in this graph right here what this means. And I actually have an example that we're going to walk through on the next slide. So if you look at the leads for normal, this is going to be up and this is going to be up. So that means that this will be towards the positive part, and this is going to be towards the positive part. And then if you draw lines in this direction, this will be in the normal range. And then for left deviated axis, what you're going to have is this lead's going to be positive because this part's up, and then the AVF is going to be negative, and if you were to draw lines, it'd be to the left. And then intuitively, that's going to be the same thing with the right. So if the AVF is up and the lead one is down, it's going to be in the right deviation. And then if they're both negative, which will be in this area here, it'll be an extreme deviation. This will make more sense when you see the example on the next slide. Again, this is called the hands method. So here's the example. Look at lead 1. You can see that it's actually, if you sum it, because you have to sum the above and below, overall it is negative. So it's -5. And then AVF, if this is up, it's going to be 6 total in a positive direction. So if you have your hands out in front of you right now, your left hand should be down and your right hand should be up. So if you can guess, this is going to be a right deviated axis because your right hand is still up. So the right hand is red, it's up. And then if you were to actually draw this out, you can see that we start with lead 1 is negative. It's going in the negative direction, which is this green arrow here. And then if you draw the positive of the AVF, it's going to go down in the positive direction here. And if you draw dotted lines here and then make a vector, you can see that it's right deviated through this black vector arrow right here. So I hope this example actually kind of explains well how to quickly do an axis deviation example by just using your hands and just using leads 1 and AVF. And as you go through it and whatever which hand is still up, that's what it's actually going to be called. So if your left hand's still up, it's left deviated. If your right hand's still up, then it's right deviated. I know I'm beating this to death, but this is a very easy thing to do if you just know the hands method. Okay, so lastly, this is called a R8 scan method. So over here, like I said before, when you're looking at all the 12 lead on the EKG, you want to look at lead 2 because this one is going mostly in the same direction as the propagation of the charge from the negative electrode to the positive electrode in the heart. So you're going to have 8 R's you're going to want to look through when you're looking at the 12 lead EKG. So first off, what you want to do is rhythm. You want to pick lead 2, and you want to see if it has a P wave, which is the red box right there. Because if it's there, that means it's sinus, meaning that the SA node is actually the one controlling the pace. And if it has a P there, then you're in what's called sinus rhythm. That's one of the first things you want to look for right there. Next is rate. Like we showed on the previous slide, how you actually do that, the 300 divided by the number of big boxes you count. You want to know if this is going to be high or low, meaning that is it tachycardic or bradycardic. And then what you want to do is you want to see the R to Rs. So what I'm saying here is if you look from here, from this tip for the R to here, is this area here the same as this one and so forth and so forth? Because if you have something like what's called AFib, what'll happen is this will be this length and they'll have like a really short one and then like a really, really, really long one. So it's going to be an irregular rhythm. And you can really pick this out really quickly if it is AFib, if they are short and long and they alternate and they're not all equal in unison together. And that's like a really quick one to pick up. I mean, the second that someone hands me an EKG and it has AFib, I'm like, boom, this is AFib because it's fairly obvious that they're not evenly spaced. And then next you want to look at the intervals. You want to look at the PR interval, the QRS interval, and the QT interval. Because this can give you hints to what could be problematic with someone's electrical conductivity of the heart. And then QRS, you want to know if it's wide or narrow, because if it's wide, it can be a certain type of pathologies versus narrow, which could be also a different type of pathologies. And I'm going to have a video on EKG examples that's going to be coming up in a couple days. And that will actually go through these examples of like wide and narrow QRS complexes. And then again, rise, where that arrow is over here, you want to see if you can see tombstones or ST elevations. Like I said, between the S and the T, at baseline, it'll be elevated and it'll look like a tombstone like this. And then any kind of resistance, meaning like, do you have any, essentially clots or clogs or plaque in the coronary arteries of the heart, and is it causing a quote unquote block? Therefore, it's having difficulty propagating the electrical signal of the heart. And these are called left bundle branch blocks or right bundle branch block. These are just examples of what kind of resistance could be there. So you want to take a look and see if these are actually present in the EKGs. And that'll actually be explained in the next video for the EKG examples. And then the last R is going to be random. So you're going to look for a delta wave, for a WPW, and then you want to look for peak T waves, which means you could have high potassium, known as hyperkalemia. And then you can look for what's called an S1 Q3 T3, which would possibly indicate someone that's having a PE or a pulmonary embolism. It's not always present, but if you do see it, it could help indicate that your patient's having a PE. So those are the 8 random R's that you're going to have, not random, but the 8 R's you're going to use to scan. And if you do it in this order, you shouldn't miss anything, and it should be pretty methodical of what you're looking for. So that's pretty much the main point of this video. So it's going to be just a little bit of a recap. So again, the basics, you're talking about positive charge moving towards a positive electrode. Then you're going to have the conduction pathway of the SA node, AB node, bundle of His, and then Purkinje fibers. We talked about the intervals of PR, QRS, and QT. Talked about determining the heart rate. Just use 300 divided by the number of big boxes. We went through all the 12 lead EKGs of 1, 2, and 3, AVR, AVL, AVF, and then V1 through V6. Talked about where's my heart attack based on the actual grid of when you look like, and then the diagram that I made, that if you guys just write that down, you should be able to figure out really quickly where the issue is with the coronary arteries of the heart. And then the hands-on axis deviation method, I think that one's really helpful. They can answer your questions really quickly. If you just stick your hands out and just look at lead 1 and then AVF and then just figure out which one's up and down, then boom, you just know that it's left or right or extreme axis deviated or normal. And then lastly, the R8 scan. I thought this was a pretty good one. I know it's going to be a little difficult to remember all the R's. Just write it out a few times, and it should stick pretty well. All right, so that's the video. I know I went through this pretty quickly. I would recommend to watch this a few more times just to really kind of hammer it in. If you want to screenshot or share or, Anki the hell out of this, go for it. So if you guys like this video, give it a like. If you want me to make more videos, I know I've said this in my past ones, then subscribe. I think I only have a couple subscribers right now. It'd be nice to get in the double digits, maybe like up to 10. So more people that watch this, even the better. So hope this really helps, gives you, a bit of a baseline before you really dive into EKGs and getting like the actual fine nitty gritty details. So I hope this helps. If you have any comments on how I made this video or how I went about it, just drop them below. And yeah, good luck studying, and I'll see you guys in the next video. Love you guys, and keep on studying hard, okay? All right, peace.